Hello and welcome to C++ Weekly. I'm your host, Jason Turner, available for code reviews, contracting, and on-site training. In this episode, we need to talk about type erasure. I'd like to thank today's sponsor, Whole Tomato. If you're looking to up your C++ Visual Studio game, you should check out Whole Tomato's Visual Assist. Visual Assist is a feature-filled plugin for Visual Studio offering a wide range of tools to help you with your everyday work. My personal favorites are the little niceties such as enhanced keyboard shortcuts like the Alt arrow that I've personally grown very accustomed to using. That helps me move forward and backward in my editing history inside of Visual Studio, as well as enhanced color syntax highlighting. But there are many different refactoring tools, editing helpers, debug assistance, and Unreal Engine support if you do Unreal development. So be sure to check out the video description for links and for more information on Visual Assist. Okay, so the main point of type erasure is to basically hide types at runtime. So the most simple example of this in C++ is simply through inheritance. Now, I've just created this base class. It's pretty straightforward. It doesn't actually have any member functions to speak of, but I defaulted explicitly all of the special member functions because I needed a virtual destructor with inheritance in C++. That is always recommended if you have virtual functions. And I made all of the other special member functions protected when I defaulted them. And there's a million different ways that you can go with this. I just did this for the sake of just illustrating the fact that we might want to consider disabling slicing. That's all. And if you don't know what that means, well, then you have a homework assignment. Okay, so I've just arbitrarily defined two derived classes. Inside of this function called useType, or I could call it useBase, I guess. I don't know what the underlying actual type of this thing is. So it could be derived, it could be derived to, it could be some yet to be defined type, it could be some type that was actually loaded from a dynamic library, and there's no way for us to reason about it. Now, I do know that some of you would say, but we can reason about this type. Because if we do a dynamic cast, then we know that, in this case, base is actually of type derived. So yeah, sure. In some limited fashion, you can reason about this, but this doesn't hold for very long because I can write a function like this. Now, inside of useBase, there's really literally no way for me to reason about this type. There's no way for me to even name my derived. This is a type that cannot be named. There's simply no way to do this. It is not possible here. This is kind of normal runtime polymorphism view of type erasure. Now, there is a classic example built into the standard library, and we touched on this a few episodes ago when I talked about standard function. This has the more complex form of type erasure that a lot of people think of when they look for the C++ version of this. And it involves polymorphism, but in a way that never affects the user. So I'll reference you back to that previous episode. But this function contains a pointer to a polymorphic type that is all managed internally. Now, the end result is to give the user of the library something that's very simple to work with. We can do something like this. We can pass a regular free function to it. We can pass a lambda to this use function. Or to really drive the point home, we can use any callable type. So in this particular case, I have declared a local struct that has a call operator overload defined. And then I am using standard bind front to take a pointer to that call operator and bind it to a pointer of this object named little s, which has been initialized with the value 42. So this should return 2 plus 3 plus 42. And there you go. So standard function is a very high level type of type erasure here. That makes it very easy from the user's perspective to work with all these things. Now, the entire point up to this point has been we have a mechanism for hiding the exact type of an object. The result of this we can work with any type that happens to support a particular interface that might be declared in the future, and we get this compilation firewall to prevent recompiling this entire library simply for allowing the user of our library to provide us with a new type that we had never seen before. Now, these techniques can be combined in many ways. So if we had templates in this case, we could do all of this without any form of type erasure. That's actually type inference. And in the case of templates, the exact type is always known that was passed to us. We're not going that route. We're turning things around. So there's another technique that is kind of building on this idea of a view that has become a little bit more popular lately. We have span and we have string view, and this allows us to pass things that support a particular interface to a function, can be very high performance, and can be very simple and help us actually reduce compile times. So I'm going to throw together a quick example here, and in fact, I might just go ahead and paste it in. So this is going to take some walking through to really understand what it's doing. I have created an animal view. Now, what we know is that this thing expects an interface of an object that can speak. So the only requirement is that it has a const member function called speak, which you can see here. Now I have declared a cow and I have declared a sheep, and they both have these speak functions. And in their speak function, they say the appropriate thing that a cow or a sheep might say. So when I go to actually use this animal view, you can see here I have this function called do animal things. It accepts an object of type animal view. This doesn't need to be a template. It doesn't need to be declared in a header file. It can be declared anywhere. It does not require polymorphism. It does not require anything of the types passed to it, except that they support this one particular interface that we're talking about. So I have my animal view. My animal view class, again, not a template or anything like that, but it does have a templated single parameter constructor, which I have made explicit to avoid accidental implicit conversions, that takes any type here. Now I have used its template and it is called speakable. And I take a pointer to this object that was passed to me. So at this point, we have to start asking ourselves questions about object lifetime. We don't want to accidentally have a pointer to an object that has gone out of scope. But I took a reference and I took a pointer to the underlying object, and I'm storing that here as a const void pointer. Now I have speak impl. Now this is the thing that does the actual work for us. It is a lambda. And if you've watched my videos on lambdas up to this point, you know that lambdas can be very helpful in many ways. And in this particular case, we're using a lambda to create a function pointer, a free function, basically. So this lambda takes a const void pointer, and inside of it, it knows how to static cast my object, which is going to end up being this const void pointer, to the actual passed in type, which is this templated thing called speakable. It might be cow, it might be sheep, we don't know at this point. And it calls the member function speak on this pointer. Now I have created a member function of animal view called speak. It is a const member function, and all it does is call speak impl. Now speak impl is this function pointer that I mentioned a moment ago, created by the lambda. So this is function pointer syntax. I am saying I have a function that returns void, takes a const void pointer, and it is called speak impl. So inside of speak, I call this function pointer, which is going to be valid for the lifetime of the program because it is a pointer to this effectively free function created for us by the lambda. I call speak impl with the object. The object comes in here to the lambda. It is static casted to a speakable, whatever the speakable templated type was, and speak is called. So the end result of actually calling this is I can call this function called do animal things. I pass it an animal view, and I'm just creating an object of type cow for the moment on the stack. And this is all safe because that object is going to live for the lifetime of this expression. And that is the same for the sheep. And we can see that moo and ba are actually printed on the console here. So another type of type erasure here, it kind of works like standard function, but kind of skips the middleman. There's no dynamic allocations, there's no complexity with small object optimizations, nothing like that. It just takes an object pointer and does something with it. As the notes here say, you do have to be careful. It's possible to end up with a dangling reference, and that's true of any view type. And we don't have any polymorphism or dynamic allocations, but we do still have a function in direction. So from a performance perspective, we've not actually gained anything over having a virtual member function called speak, because the compiler is still going to have to do a pointer in direction to dispatch to that function call. However, we have made it much simpler to use our library. I don't know, something to think about. Obviously, there will be links to this in the video description, so be sure to check those out if you find this topic interesting. And thank you for watching this episode of C++ Weekly. Hope you enjoyed it, and be sure to subscribe. I just realized that before I let you go, I should point out what the actual implementation of do animal things is. So this is do animal things. It takes this animal view. And if we look at the actual optimized compiled code, this is it. Do animal things is a single instruction. It does a jump to RSI. And RSI is the second member of our animal view object, which is this member function pointer. Basically, it just fully inlined all of this, calls the function directly. That's really pretty cool. So anyhow, be sure to subscribe.